First of all, this is Part C, Section 13.1, Part C. And the fact that we have just discovered that it doesn't matter which order we choose to do our integration can really be used to our advantage. Sometimes we'll choose our order of integration in order to make an integral either easier or even simply possible to evaluate. Here's an example in Example 3. Suppose I'd like to evaluate the double integral over the region R for this function, and R is the rectangle where x goes from 0 to pi thirds, and y goes from 0 to 1. Now, as I look at this, the differential here, dA, could be either dx dy or dy dx. I get to choose. So, as I'm thinking about this, I know that I have a way of integrating the secant squared function, right? The integral of secant squared of something is tangent. So that part's not going to be too bad. But since I don't just have a simple single variable inside the secant squared, I'm going to need to use a U substitution. Let's let u equal xy. Now this is where the strategy comes in. If I take the derivative of u with respect to x, I'm going to get 1y. And I don't have a y out here to work with. However, if I take the derivative of u with respect to y, I'm going to get x times 1, or just x. And I do have an x out here to work with. So it's going to be better for me to do the y derivative, meaning I'm also going to want to do the y integral first. So let me start by rewriting my integral. And based on the logic we just talked about, I'm going to choose to do dy first, and then dx. The y goes from 0 to 1, and the x goes from 0 to pi thirds. All right, I'm going to finish my U substitution piece. We're doing the y, so the partial derivative of u with respect to y would be x times just 1. And therefore du is equal to x dy. One thing I'm going to ask you not to get too involved in is the partial derivative notation compared to just the differential d notation. We do get a little sloppy with those, and we kind of use them interchangeably. They both just mean differentials. And typically in the integral notation we have the plain d's, which is why I switched here. By the way, I apologize. When I'm making these videos, I will hopefully not have my dogs bark too often. All right. I have an x dy right over my integral. So I'll make my U substitution and replace that x dy with the du. So I still have this outer integral from 0 to pi thirds, saving it for later. And now my inner integral becomes the secant squared of u. And instead of x dy, I'm going to put in the du. I still have this dx out here, again, saving it for later. Notice I'm not going to put limits of integration in right now. I'll put them in later. They refer to the y variable, and I don't have a y variable right now, so I don't want to use them at the moment. All right, the integral of secant squared u du is just tangent of u. And now I can put back u is actually xy. And now finally I've got my y variable back. Y was supposed to go from 0 to 1. All right, back on solid ground, we'll use our fundamental theorem of calculus. Plugging in y equals 1, I would have just the tangent of x, x times 1 being x, minus the tangent of x times 0 is 0, dx, or simply the integral from 0 to pi thirds of tangent x dx. All right, with a little bit of help probably from a table of integrals or something like that, we actually do know how to integrate tangent x. But something I'm going to tell you and we'll do from this point forward is when we get down to a single integral, that's something that our calculators do really well. So once you get down to a single integral like that, you're welcome to finish with your calculator. You simply have to get that first integral done by hand to get to the point that the calculator can handle it. So, probably can't see the calculator great on my screen, but you can do it on your own. If I simply go to Math 9, on my TA84 at least, and I do my integral from 0 to pi thirds of the tangent of x dx. And I'm getting, oh dear, you know what? I probably didn't check my mode. I did not. I was in degree mode, and I should not have been. Let me go back and do that one more time in radian mode. That's much better. Looks like I get about 0.693. I think that's ln2, yeah. Sometimes you recognize those numbers. It happens to be exactly ln2, but I'm fine with the decimal approximation if you do the problem on the calculator. Unless the instructions for a problem specifically say you must do all steps by hand, you are welcome to use the calculator to finish that last single integral. All right, let's do another problem similar to this. We have y over x plus y is our integrand, and it's written in the order dy dx. I don't love that order because you'll notice there's a y on both the top and the bottom, which makes it much more complicated. In fact, if you remember back to Calc 2, we'd probably want to do some sort of a long division thing, since the degree of the top and bottom are the same, where y is concerned. I would be much happier if I could integrate that with respect to x. There's only one x, it's on the bottom, probably going to end up with some kind of a natural log, but I think it's going to work out pretty well. So, let's choose to reverse this. Let's choose to do the x integral first. Now, since I reversed the order of the integration, that means I have to reverse the limits as well. I'm now doing dx first, and the x's went from 1 to 2, and then I'm doing dy second. The y's actually went from 1 to 4. All right, now that I'm looking at this with respect to x, the numerator is just a constant, which doesn't bother me. So I'm going to let u be the denominator, x plus y. And I'm doing an x integral, so I also have to do an x derivative. The partial derivative of u with respect to x would be 1, plus the derivative of y, since it's constant, would be 0. So du is simply equal to dx. So I have the integral of y over x plus y, which is u, dx, which is du, and that dy is still out there waiting its turn. Now, if this is bothering you, let me do a quick rewrite to remind you it's not that bad. Y is a constant multiplier, and I could rewrite that as y times 1 over u. As far as this integral is concerned, as far as u is concerned, y is just a number. It's like 4 or 7 or something. It isn't affected by this integration. So this integral, I still have the constant y. The integral of 1 over u du is the natural log of u. And the dy here is still waiting its turn. By the way, some people even like to take this y and pull it right out in front here. And if that makes that integral right there look better to you, certainly feel free to do that. All right, so I have the integral from 1 to 4 of y times the natural log of, and I'll replace the u with the x plus y. My x values went from x equals 1 to x equals 2. All right, plugging in my fundamental theorem of calculus, I have y times the natural log of 2 plus y, subtract y times the natural log of 1 plus y, dy. And I'm very happy that I don't have to do that one by hand because that would not be a fun integral to do. But again, I'm just going to invite you to get out your calculator and finish that integral using technology. And I'm coming up with about 1.828. All right, one more practice problem in 13.1. Example 5 here. We're looking for the volume of the solid beneath this paraboloid. Notice 12 minus x squared minus 2y squared is just a paraboloid that's been shifted up 12. And because of the minuses, it's upside down. We also want to stay above the region, x going from 1 to 2, and y going from 0 to 1. So you can kind of see down here in the base, they've highlighted a little bit. There's this little base here where x is between 1 and 2, and y is between 0 and 1. Going directly above that rectangle, they ended up with this curved piece of the paraboloid as the kind of ceiling or lid on their shape. And we're finding the volume of this whole solid in between there. All right, let's set up our integral. To find the volume, we do the double integral of the function, the height, 12 minus x squared minus y squared. We always integrate the height function. And then I'm going to decide whether to do dx or oh, excuse me, that was a 2y squared. Let me fix that. There we go. I'm now going to decide whether to do dx dy or dy dx. And honestly, when I look at the integrand, it really doesn't matter. It's no easier or harder to integrate first with respect to x or with respect to y. There's very little reason for me to pick one over the other, but maybe just basic laziness. I like the 0 as the limit of integration on the y. Zeros are so easy to plug in. So maybe I'll do dy first, so that the one I get to do by hand has the 0 in it. I'll do dx second, and that one goes from 1 to 2, but I'll eventually be using a calculator to do that. All right. So I take that first integral, just save it, and then integrating dy. The constant 12 integrates to 12y minus the constant x squared times y, minus 2y cubed over 3, or 2/3 y cubed. And that goes from y equals 0 to y equals 1. Plugging in the y equals 1 first, I'm going to have 12 minus x squared times 1 minus 2/3 times 1. Subtract, plugging in y equals 0 is going to make all of those 0. And I'm going to integrate that dx. You could combine those constants if you wanted to, but honestly, the calculator doesn't really care. I'm going to go ahead and just plug it into my calculator just like that. I want to integrate from 1 to 2. My function, And let's see, I just got a 9 this time. So the volume of that piece is 9. All right, that concludes section 13.1. And I've posted for you a 13.1 worksheet. So I would encourage you to spend a few minutes, try those problems, see what you can do with them. And when you're comfortable with this section, come on back for 13.2.